and then we'll. Okay. So what I was saying is step 1 was to factor, see if we could simplify. It did not simplify, so that means there's no hole. Okay, if there was a hole, there would have been a factor that reduces, and then you would have set that equal to 0 to find out where the hole is. All of that is listed specifically on your step sheet, that reference page I gave you. Okay. If there was a hole, you would plot it like a point, but it would be an open circle instead of a solid point. All right, now step 2 says to find the y-intercepts, or intercept, excuse me. You're not going to have more than one y-intercept. It wouldn't be a function. Okay, how do you find the y-intercept? Give your notes. Give your notes. 6.1, and you need your step sheet out too. Anybody see on their step sheet? What does step 2 say? Yep, so we're going to find f of 0. If you're finding a y-intercept, if you're on the y-axis, x must be 0. So you're plugging in a 0 for x. So you can do that in the original equation before you factored here. Since nothing reduced, you can still keep using the original equation. If something had reduced, we would need to make sure we're using the new reduced equation. Okay, so this is going to come out to 0 over 1, which is just 0. So when I input a 0, I get an output of 0. So there's a point at 0, 0. So I'm going to graph that. All right, now, can anybody just venture based on that to tell me where an x-intercept will be? Also at 0. If you're at the origin, you're on both the x and y axis, right? So if there's a intercept that you find at the origin, you better find it for the other intercept as well, or you've done something wrong. Okay, so for x-intercept, what does it say to do? How do we find those? Y'all should all have your step sheet in front of you. Set the numerator. N of x, remember, stands for numerator. So we set the numerator equal to 0. In this case, we already factored it in step 1. So I'm going to go ahead and use that factored form to save me having to refactor it. So I'm ready to split and solve. Okay, so this one's already solved for x. Here I would have to add the 1 over. So these are the x values of the x-intercept. So as coordinates, that would be 0, 0, and 1, 0. So I have 2 x-intercepts here. I'm going to plot that second one. The first one's already plotted in orange. Okay, what's step 3? Okay, or I'm sorry, we just did step 3. Step 4. What does it say to do for step 4?
Asymptote.
What kind of asymptote? Vertical. So we want to find the vertical asymptote, and how do we do that? Good. D of x, that's the denominator. You set that equal to 0 and solve. My denominator is just x plus 1. So when I solve that, I get x equals -1. Now this is not a coordinate. This is an asymptote. It's a line, okay, a vertical line in this case. So I leave it as it's written as an equation, x equals -1. That is my vertical asymptote. So that's what I'm going to plot on my graph. I draw my asymptotes as dashed lines. So where x equals -1, we have a vertical line. So far, so good? Okay. All right, what is step 5? Okay, see if there is a horizontal asymptote. And how do I do that? What does it say to do? on your step sheet, what does it say? Look at the degree in the numerator, which is n, and the degree in the denominator, which is m, and compare them. Okay, so here's my original equation since nothing reduced. What's the degree in the numerator? 2. What's the degree in the denominator? An understood 1 since there's nothing there. Okay, so how does n compare to m? Are they equal or which one's bigger? N is greater than m. And what does it say on your step sheet when n is greater than m? There is no horizontal asymptote. Okay. Step 6 then is to find your slant asymptote, if there is one. How do you know if there will be a slant asymptote? We need to know, does n minus m equal 1? Is the numerator's degree 1 higher than the denominator's degree? And in this case, it is. 2 minus 1 is 1. This is 1 higher than m. So we do have this here that does equal 1. So I know there is a slant asymptote. Now to find out what the slant asymptote is so that I can draw it, what should I do? You can look at your step sheet to see what it tells you to do. You can do long or synthetic division, and you should get what? What type of equation should we end up with? Linear. Okay, it should be a line, just y equals mx plus b form, right? So synthetic, I think, is easier. So I'm going to show you with synthetic. Okay, remember we have the little box out here. We'll have a list of our coefficients, and then we'll draw this line. Okay, so let's set this up. What goes in this little box? How do we find what goes here? Yeah, it's the denominator set equal to 0 and solved, right? So in this case, didn't we already do that in step 4? We set the denominator equal to 0 and solved. So when we're doing rational functions, if you've already found your vertical asymptote, you can just go back and look at that. That's what's going to go in this box. Okay, so -1. And then what is listed here? The numerator's coefficients, right? Just the numbers. Okay, in descending order. And we have placeholders when needed. So this is a quadratic. So you should have an x squared, an x, and a constant term. So there should be 3 numbers. So what's the coefficient of x squared here? Understood, 1. What's the coefficient of x? Yeah, it's -1. And is there a constant here? So we put a 0 as a placeholder. So we're going to have 1, -1, and 0. Okay, so now we start the synthetic division process, which is drop the first term below the line. It doesn't change. And then you multiply this. -1 times 1 is -1. And then you add. And then -1 times -2 is 2. And then you add. Okay, now what is this that we got? What is this telling us? That last term is the remainder. Good. Do we care about the remainder when we're trying to find the slant asymptote? No, we said in the 6.2 notes at the very end. You can go back and read that. When we're looking for a slant asymptote, that's the reason we're doing synthetic or long division. We don't care about the remainder. It does not affect our slant asymptote. Our slant asymptote is going to be in the form y equals mx plus b. Okay, and what you get, so you should have 2 numbers here, and that's your m and your b. That's your coefficient of x and your constant. So my slant asymptote is just x minus 2. Is everybody okay with that? Do you remember how to graph a line? Where do you start? With the y-intercept, right? -2. And then what do you count from there? Yeah, you count your slope, which is that 1. So it's just up 1 over 1, up 1 over 1, up 1 over 1, because it's a +1 slope. So start at -2 and count a +1 slope. You can see this is the slant asymptote. You can do it just as little dots like this, like it's a dotted line, or you can draw the dashes and make it a dashed line. I really don't care how you do that, as long as you can see where your slant asymptote is. The whole point of the slant and horizontal asymptotes are to guide your end behavior. End behavior is the left and right hand ends of your graph, right? That's what the slant asymptote is there to do, to guide the ends of your graph on where they're supposed to be going and like at how steep that should be. A horizontal asymptote would be the same thing. Okay. All right. So then step 7 says test interval chart. We have not done that yet because we hadn't done examples where we're graphing the whole thing with all the details. But what a test interval chart is, it can be more complicated. You can make it more detailed, but I'm going to try and keep it simple and just do an XY table instead of a big chart. Okay, and you are just going to pick X values. You pick the X values to check. Okay, and then we'll find out what their Y is, and then those will be additional points for us to plot to help us sketch our curve. Okay, now, what values should you pick, or how do you go about picking, is use your vertical asymptotes and zeros. Look at your x-axis, because you're picking X values. So pick values to the left and right of your asymptotes, or in between your asymptotes and zeros. Does that make sense? So I've got a vertical asymptote at -1. So to the left of that asymptote, I don't have any points plotted. I don't know where my graph is over here. So I'm going to test -2. And I'm going to see, should I be up here in this sector between the asymptotes? Or should my curve be down here in this sector between the asymptotes? Do y'all see what I'm doing? I'm going to test -2 and see where I end up so I know where to draw my curve. Okay, now when you're testing a point, you are plugging that value into the equation for X. So I'm coming back up here and I'm saying -2 squared minus -2 over -2 plus 1. You get a scientific calculator on your test. You can do that math in your calculator. You don't have to do it by hand. Okay, I'm going to save us some time and just tell y'all what we come out with these test points. Okay, but that's what you're doing. You're plugging it in to the equation to see what Y value you get. So this comes out to -6. So that means there's a point on our graph at -2, -6. So then you can plot that point. So that tells me, okay, to the left of this vertical asymptote, my curve is in this little sector. Okay, and then the vertical asymptote and the slant asymptote guide the direction that it goes. So it's going to follow along the asymptotes and come through this point. So there's going to be a curve there as part of that rational function. Now, I can see without testing another point that there's going to be a curve in this sector because that's where my zeros are, right? And obviously, if I have 2 zeros, I must cross the x-axis and turn and come back through it right there. You could pick test points and you could test a point between the zeros and between the zero and vertical asymptote. Okay, so you could do that, but I'll just tell you, you're going to get one about here, about here, and about here. That's just going to guide your curve along the asymptotes through those zeros. Okay, so it's really not necessary to test additional points right there. Now, if you're curious, well, what about this sector? Is this sector going to have a curve? What do you know about a function? It has to pass the what? The vertical line test. So if this is following this asymptote and it goes out forever, am I allowed to have something else under here when this curve is above it? That would fail the vertical line test, wouldn't it? So you couldn't do that. This wouldn't be a function if that happened. So because I know there's a curve up here, I really don't have to test another point. If you didn't realize that and you wanted to test a point to the right of that zero or to the right or under that slant asymptote, you're welcome to. So you could test, like we could test a 3. We could say, well, what about at 3? Where should this graph be? Should it be down here below this asymptote or should it be above it? So you could, we would do 3 squared is 9 minus 3 is 6 over 4. So that'd be at 1.5. So we know there's a point at 3, 1. And hey, look, I did good drawing my graph because that's where it would go through. Does that make sense, guys? So the test interval chart is just to help you get additional points to figure out where your curve is supposed to be drawn. Because with just your intercepts, sometimes that's not enough to know where the rest of your curve or curves should be drawn. Questions so far? All right, so we're going to repeat that process on example 4. I'm actually going to make an edit here, though. I did it this way, worked out this way with my other 2 classes this morning, but this numerator does not factor. And so you can't, when you try to set the numerator equal to 0 and solve, it doesn't factor. We try quadratic formula. We get a negative under the root. It doesn't work. You can't solve this numerator, which means there are no x-intercepts. Okay, so I'm going to make just a side note here because I'm going to change this and we're going to use a different one that we are going to be able to calculate some stuff. So I'm just going to make a side note. If you cannot solve your numerator equal to 0, so if it's unfactorable and you try quadratic, I'm not going to give you one where you have to try quadratic formula, but if that happens, what that means is there are no x-intercepts. That's all it means. It means that graph doesn't cross the x-axis. Okay? So far, so good? All right, so let's make an edit though so that we can do this. So let's make this a 2 instead of an understood 1. So minus 2x. Good? So that's what I want to use now. So we edited that to make it minus 2x instead of just minus x. So step 1, going to factor the numerator. All right, so what do we get here? The factors of 1 are 1 and 1. And if we want them to multiply to a positive, they have to be the same sign, either both positive or both negative. If we want it to add to a -2, they must both be negative, right? Oh, so interesting. I have lots of x minus 1 factors. So when I talk about reducing, are all of those going to reduce? No, not all of them, because there's only one in the denominator, right? It can only reduce with one of the ones from the numerator. So even though x minus 1 is there twice, you only get to reduce one of them. Y'all with me? So this reduces to be just x minus 1. Okay, that's what I call my new equation. Okay, my reduced equation. Okay, now because that reduced, what does that tell you? There's a hole. So to find the hole, you set the reducing factor equal to 0 and solve. So we get positive 1, right? So the x value of the hole is at 1. Now I need the y value. What do I do to get the y value? I plug it into the new equation. The new equation is y equals x minus 1. So if I plug in a 1 minus 1, I get 0. So there's a hole at 1, 0. So I can go ahead and plot that. Oh, I went up 1, excuse me. At 1, 0, an open circle. That's a hole. All right, now step 2, I try to find my y-intercept by calculating f of 0. That's to the new equation. So 0 minus 1 is what? Just -1, right? So the y-intercept is at 0, -1. Okay. Now I want my x-intercept. Now, x-intercept comes from setting the numerator equal to 0. Well, my numerator is still x minus 1. So I get x equals 1 again. Same thing I got for the whole, because those factors were the same. Do you see that? That's why those came out the same. But do I actually have an x-intercept at 1? No, it's a hole. There's a hole there. So this means there is no x-intercept. Okay? Because there's a hole where it should be. Mm-hmm.
Yeah, maybe some wrong there. If y equals 0 minus 1, then it 1.
0 minus 1. So if think about the number line, if you're at 0 and you minus 1, that means you go to the left one. So you're at -1. So are you talking about this right here?
Yeah.
Yeah, if you have 0 of something and you take away 1, you're in debt 1.
0 minus 1.
Uh-huh. No, I plugged in because the equation is x minus 1. That's the new equation. And so I'm plugging in a 0. So if I plug in a 0 for x, here, maybe if I put parentheses, I don't know, that'll make it more clear. I plugged in a 0 and then I subtract 1. I'm at -1.
Yeah,
Does that make more sense?
Yeah, they're like,
Oh,
like add the one to the other side.
oh, no, no, no. All right. Okay, so that's okay. Step 4 is to see if there's a vertical asymptote. Now, vertical asymptote would happen where your denominator equals 0. Do we have a denominator anymore? The new equation doesn't have a denominator. There is no d of x, so that means there is no vertical asymptote. Okay, step 5 is to see if you have a horizontal asymptote. That's where you compare n and m. Well, the degree in the numerator is all understood 1, and there is no denominator. That's what we just said. So the degree of the denominator is 0. It doesn't exist, right? So n is greater than m, so there is no horizontal asymptote. Okay, you only have a slant asymptote if n minus m equals 1, but this is a special case. 1 minus 0 does equal 0, but we're not going to have a slant asymptote because there's not a denominator. There's nothing to divide, right? Y'all understand that? There is no slant asymptote, and that's also due to the fact that there's no denominator. There's nothing to divide. We can't do synthetic division or long division. There's nothing to divide by. So no slant asymptote. Now, some of you may have seen this at the very beginning. Some of you, I still wanted to go through this so you could see how it works out. But let's go back and look at that new equation. What type of function is this new equation? It's just a line. This graph is just a line through these two, this point and hole. It's got a slope of 1 and a y-intercept of -1. Okay, if you want to do a test interval chart and come up with additional points to plot, you're more than welcome to. If I test 2 or I test -1, okay, if I plug in a 2, 2 minus 1 is 1. If I plug in a -1, -1 is -2. You can get additional points. There's a point at 2, 1. There's a point at -2, or excuse me, -1, -2. But you can see, isn't this just a line? Y'all see that? If I connect all these, it's linear with a hole. There's no asymptotes. It's just a line with a hole in it. That's what it's simplified down to at the very beginning when we reduced that. We just got a line with a hole. Does that make sense? That came out linear, which just graphs a line. All right, now I am going to show, since I'm recording this, if in case you're watching from one of the other classes and you're looking at somebody else's notes, if we did not change this at the beginning, if we didn't change that to a -2x there, if we kept it the original equation that was typed there, I'm just going to point this out. This is what it would have ended up looking like. And we said you cannot factor, so there would have been no holes. And because you couldn't factor on step 3, you would have had to try quadratic formula, which doesn't work because you can't take the square root of a negative. So there's no x-intercepts. It doesn't cross. Okay, and you could have done everything else, and there would have been a vertical asymptote, and there would have been a slant asymptote. We would have had a graph similar to the one that was graphed in example 3 above. Okay, So that's there. You can pause the video and look at that in more detail if you're interested. Okay, but I wanted to show y'all something different since that's pretty similar to the example above. And I'm not going to give you one that does not, that you can't solve and would have to use quadratic formula. So far, so good. All right, last one. Okay, this one's a much bigger graph here because we needed some of these higher numbers to plot some points when we get there. Okay, so step one, we're going to factor to see if we can simplify. The top does not factor. The bottom does. The denominator does. What are factors of negative 12 that add to positive 1? Okay, positive 4 and negative 3, right? That would multiply to negative 12, but add to positive 1. Okay, so here's factored form. Does anything cancel in the numerator denominator, or reduce, I should say? So what does that tell me? No holes. Okay, so then I move on to step 2. Y-intercepts. By plugging in a 0, I'm plugging in 0 for all the x's, and I can use the factored form or I can use the original form since nothing reduced. I can go back to the original. So if I plug in a 0, I end up with 0 over 12, which is, so I've got another y-intercept at the origin. So I can plot that point. Okay, x-intercept is step 3, and that is found by setting the numerator equal to 0. Well, my numerator is just 2x cubed. How am I going to solve for x there? Divide by the 2, which is still 0 divided by 2. Still 0. And then how do I get rid of the cube? Take the cube root, and the cube root of 0 is 0. And I should know before even starting that I should get 0 because the y-intercept was the origin. And we said if the y or x-intercept is the origin, the other one has to be as well. Now there can be more than one x-intercept, so we still needed to check and see if there was another one, but there wasn't. All right, next up is vertical asymptotes by setting the denominator equal to 0. Now in step 1, I already factored, so I'm going to use that factored form. X plus 4 times x minus 3 equals 0. And I'm going to split and solve. I set each factor individually equal to 0, because if either one of these is 0, the whole thing is 0, right? Because 0 times anything is 0. That's the whole reason we split and solve. So we could say, what would make x plus 4 equal to 0? A negative 4. What would make x minus 3 equal to 0? A positive 3. So I have 2 vertical asymptotes this time. So I'm going to graph both of those. Okay, and I know they're tall. We're going to graph it all. Okay. What's after vertical asymptote? Horizontal. What is in? Go back and look at the equation. What's the degree of the numerator? What's the degree of the denominator? 2. Okay, remember it's the highest power when it's not factored. If you're given the equation in factored form, you would have to look at the first term of each factor and what would you get if you multiplied them all together? Okay, but this one is in unfactored, that's 3 and 2. So again, n is greater than m, so still no horizontal asymptote. So none of these examples had a horizontal asymptote, but how would you graph a horizontal asymptote if there was one? What would it look like? Yeah, it would be a dashed line, just like we were doing for the vertical and the slant, but it would just be horizontal. It'd be flat left to right. Okay. And it would go through when y, so it'd be y equals a number, and it would just be a horizontal line. Okay, this one does not have one, so we now look for slant asymptote. Does n minus m equal 1? Yep, 3 minus 2 equals 1. It sure does. So we know we have a slant asymptote, so we're going to divide. You can do long division or synthetic division. Okay, so I'm going to set up synthetic. Now this one is going to be a little different than you've seen. So let's take a look. We'll have our little box, have our line. Okay, what's listed here? What gets listed here? The numerator's coefficients, right? Just the numbers. Okay, so it starts with x cubed. The coefficient is 2. So 2 will be the lead term. But what about x squared? Is there an x squared term? Yeah, put a placeholder. Is there an x term? Put a 0. Is there a constant? Put a 0. So I have to have 3 placeholders here because there's only the x cubed term. I need the x squared, x, and constant. Okay. Now, here's where it's different than what you've seen before. What goes in this box usually? It says you set the denominator equal to 0, right? And solve. And we did that, we said in purple here in step 4, and we got 2 solutions. So what's going to happen is you're going to have to plug both of these in, but we're going to do it one at a time. It does not matter which one you do first. So I'm going to just do -4 first. Okay. So I'm going to do my synthetic division process. -4 times -8, so 32. -4 is -128. Now, we said that this last term is the remainder. And do we care about the remainder?
No.
Not for slant asymptote, we don't. Okay, is this linear yet though? No, there's 3 terms here. This is quadratic. You've got x squared, x, and constant. So this is what makes it different. We are not done yet. We're going to have to continue our slant, finding our slant asymptote by continuing our synthetic division. So the other value that we're going to plug in that little box is a 3. So now we're going to use the 3. And we're going to repeat or continue, I should say. We're not starting over with the 2, 0, 0, 0. We're going off of what we found. Okay, so I dropped the 2 down. 3 times 2 is 6. That's -2. 3 times -2 is -6. So that'd be 24. But again, for this set, that is our remainder, isn't it? Agreed? Oh, yes, it would be 26. Sorry. Okay, but do we care about that remainder? No, we don't care about the remainder. Now it's down to a linear function, right? Because this started as x cubed. We divided out one of the factors and got it down to x squared. And then we divided out the other factor, and now we've got it down to x. Do y'all see that? So this is 2x minus 2. And remember, your slant asymptote should always be linear. It should be in that form, mx plus b. So I'm going to graph that by starting with the y-intercept at -2, and I'm going to have a slope of 2. So rise to run 1, rise to run 1, or fall to left 1, down to left 1, down to left 1. Okay, but you can see where that slant asymptote should be. We'll continue it up here. Rise to run 1. All right. Does everybody feel okay so far? Now, what's tricky about this one? What's different? When I get down here to step 7, my test interval chart's actually going to be pretty important because I only have 1 point plotted, don't I? I have no idea what this, I know where the asymptotes are. I know where this one single point is, but I have no idea where the curves are supposed to be here. So I'm going to test some points. I'm going to test points left and right of my vertical asymptotes and in between the asymptotes and that 0. So I'm going to test 4 points on this one. All right, so to the left of this asymptote's at -4, so I'm going to test -5. Okay, and then a point between 0 and -4. So -1 is going to be the easiest one to check. And then between 0 and 3, 1 will be the easiest one to check. And then to the right of 3, 4 will be the easiest one to check. Are we agreed on where I came up with those numbers that I'm going to test? All right, so I'm going to save us some time and just give them to you. You could use your calculator, a scientific calculator, to calculate them. Okay, and now I'm going to plot them. So at -5, -31 and a quarter, that's not even on my graph, right? It's going to be way down here, wouldn't it? Okay, but I can see it would fall in this sector between these two asymptotes, wouldn't it? So that tells me that my curve is between these two asymptotes because that's where my function exists here. It's below the slant asymptote, but left of the vertical asymptote. So it's in this little sector created here. Does that make sense? Okay. Now the other point, so -116. And so that's just above the x-axis here. And then at +1, -1/5. So that's just below the x-axis here. And then at 416. Okay, so that one tells me over here to the right of this vertical asymptote, my graph exists up here. So again, it's guided by these at the vertical and slant asymptote guide it. The whole point, the entire point of the slant and horizontal asymptotes are to guide your end behavior on the left and the right hand ends. Okay. Now in the middle, the slant and horizontal asymptote really don't matter. The slant and horizontal asymptote don't affect the center part of your graph in between the ends. They're just guiding the ends. So it looks like these 3 points should connect, but a lot of people get tripped up. They're like, well, I can't cross this slant asymptote. I can't connect these, but you actually can, okay? The vertical asymptote's going to guide the behavior there. Then it's going to come through those points and follow this one down. Okay, so I'm going to make a note down here. You can cross a slant or horizontal asymptote in middle area of the graph. They are there to guide, or guiding, I should say, the way that I wrote this. Scrolling up, come on. Okay, so they are guiding end behavior. So if you have a slant or horizontal asymptote, it is only there to help you with the end behavior. It's telling you where the left and right hand ends are going, how to sketch the graphs on the left and right hand ends. You can cross them in the middle. You cannot cross a vertical asymptote. That's the only one, okay? All right, have a good lunch. We'll be practicing this tomorrow. If you're behind on any work, that's what you can work on. No new homework though.
Am I good to get in?